On January 9, 2026, user Varun Neil posted this message on Twitter. Just realized that the greatest accomplishment of modern nano-GPT, the invention of Muon, is due to fast inverse square root via Newton-Schulz. Muon refers to the Muon optimizer, currently the state-of-the-art machine learning optimizer used at large scale. Fast inverse square root is a famous algorithm used in the 1999 Quake III game that has gone pretty viral for having some very weird-looking code. I was very curious what Varun was referring to, so I dug around a bit. And after a few searches, I came across the Modula website, where sure enough, I found the exact formula used in Quake III's fast inverse square root algorithm. Turns out that the same mathematical trick used to calculate lighting reflections in a 1999 first-person shooter helped drive ideas behind the training of the world's largest neural networks. But instead of normalizing 3D vectors for rendering, Muon uses these iterations to orthogonalize massive weight matrices, forcing them into a specific geometric alignment. And with that in mind, this is how fast inverse square root ended up in machine learning's state-of-the-art optimizer. As a starting point, let's review the gradient descent optimizer. Gradient descent is intuitively like rolling a ball down a hill to reach the lowest point. Or, more accurately, you take steps down a hill, since the process is discrete. The hill represents some chosen loss function, where lower measured values are quote-unquote less bad, so hopefully more good. Mathematically, we take a step towards the negative gradient of our loss function, scaled by some number eta called the learning rate. Here, the negative gradient represents the direction of steepest descent for a linear approximation of our loss function at that point. If x and f of x are both 1D real numbers, this is simply the direction of decrease for the tangent line at the point xn. In higher dimensions, the linear approximation becomes a tangent plane, or higher dimensional tangent space instead. Let's take a different perspective on gradient descent. If we want our loss function to be interesting, then it will be nonlinear. That means that the linear approximation that is local to the current point will get more and more uncertain the further out we go. The trust region is a subset of the whole feasible set for optimization, where, as the name suggests, you trust your approximation to be reliable. If we take our original optimization problem and instead replace it by a local linear approximation for our function, the first-order Taylor series, we would have something like this. So our goal is to minimize this unnormalized directional derivative. Except, if we didn't constrain the size of the increment delta x, a generic linear function is unbounded below and above. You can just keep going down and down, and the more and more inaccurate it gets to the original function. So, we impose a trust region constraint, and we see what gradient descent is really doing. It's solving a simplified version of our original problem, replaced with a local linear approximation over a norm ball as our trust region. The minimizer is a normalized gradient descent update, which achieves the following value. Now we're ready to tackle Muon. The problem with most modern optimizers like stochastic gradient descent or ADAM-W is that they are vector-based optimizers. In other words, they treat your parameters as completely independent real numbers. But for matrix parameters that represent linear transformations, maybe we can make use of this additional structure to design a better optimizer. How do we create gradient descent, but for matrices rather than plain vectors? First, in order to talk about a trust region defined by a norm, we need to define what a norm even means for matrices instead of vectors. For our purposes, the norm of an object basically measures its size. For inspiration about the matrix case, let's briefly remind ourselves of what a norm looks like for plain vectors. In our example of vector gradient descent, we are using the Euclidean norm, which measures length via the Pythagorean theorem. This is the only vector norm that doesn't depend on the rotation of the vector up to a positive scaling factor. What about matrices? These are two main perspectives that we can take. First, we can treat a matrix like a plain vector. if we just look only at the numbers and ignore its behavior. This is how we define the Euclidean norm for matrices, called the Frobenius norm. But that doesn't truly capture everything about it, because a matrix really encodes a linear function in some basis, not just the components of an arrow in space. A function turns some inputs x into some outputs y. So if we want to fully capture its size with a norm, then we also take into account the effects of its action on the sizes from its inputs to its outputs. In ML, x and y are vectors, so we can take a look at the norms. Here's the definition of an induced operator norm. We take the norm of the output and divide it by the norm of the input. And then we pick the worst case that has the biggest ratio. So, this definition can capture the full size of the transformation, since we can always bound the norm of our output at any point using the norm of our input and the operator norm. But for a general function, this is unfortunately intractable to actually compute. For instance, if I make up a function that is 0 everywhere, except at x equals 1, where f of 1 is 1 million. Even if you sampled 1,000 random points on the real number line, you would probably think that the operator norm is 0, but it's actually forced to be 1 million because of a single point. However, for matrices specifically, the crucial property of linearity is what makes this work. For a linear transformation L, we can pull out any scalar c and get the same value. Because we can factor out the scale, knowing the value of a single non-zero point along any line determines the value of each point on that line. So the problem becomes infinitely easier. It's enough to sample just a point in every direction. To make our life easy, we can fix the scale to a norm of 1. Therefore, the Muon optimizer focuses only on parameters of linear transformations inside our machine learning models, because it's easier to predict the size of the numbers we are working with compared to nonlinear layers. Now, let's see how we do gradient descent on matrices. Consider a single linear layer. For fixed input x and weight matrix W, the layer output is y equals wx. During optimization, we update w to w plus some increment delta w. Since the map is linear in w, the induced change in output is exactly delta y equals delta w times x. Now impose a trust region constraint directly on the outputs. Using the operator norm induced by the chosen vector norm, we can upper bound the output change, so if we can assume the input norm is bounded, then controlling the operator norm controls the output norm automatically. The motivation given by the creators of Muon is a Lipschitz constraint in deep networks. In this view, we bound the output norm on each layer recursively. If we analyze a single layer in isolation and assume the upstream activation is bounded due to the previous layers, then a constraint on the operator norm is sufficient to guarantee a small output change at that layer. In my opinion, this story is incomplete due to several issues. First, the nonlinear layers break the linear layer only Lipschitz accounting. The recursive bound only composes operator norms for linear maps. But real networks include nonlinearities, such as GELU, softmax, and normalization. Second, even if you assume your nonlinearities are Lipschitz, the composed bound quickly becomes extremely loose. Let's say each block has a Lipschitz constant of at most Li. Then, the network level bound scales like the product of Li. In a deep model, this product can explode, so the resulting guarantee on the norm of f of x or on output sensitivity becomes vacuous, even if each Li is only moderately greater than 1. In other words, the bound is mathematically correct, but so loose that it stops reflecting the actual behavior of the network. Third, naively enforcing a meaningful global Lipschitz bound is ineffective in practice. A later paper by some Muon authors, training transformers with enforced Lipschitz bounds, illustrates this directly. Enforcing Lipschitz constraints on transformer components, including nonlinear parts, severely hurts performance unless the allowed bound is made astronomically large, defeating the original purpose of the bound. I think that the more direct viewpoint is that the loss depends on output, not parameters. Let's recall the role of a trust region. A trust region is a subset of the domain of your loss function where you can quote-unquote trust the linear approximation to hopefully be accurate. But the domain of the training loss is defined on the outputs, that is, the predictions on the dataset, not on parameters. In vector gradient descent, you directly evaluate the quality of your points for the loss. In contrast, for a function layer, the loss is measured based on the outputs, not the parameters. The dependency chain goes from your input to your output and then to your loss function. As an analogy, think of the parameters as a steering wheel angle on a car. The same small turn can produce very different trajectories depending on the model of the car, and different cars may require different steering angles to follow the same path. What matters for performance is that the path the car takes, which would be the model outputs on the data, not the steering wheel coordinates themselves, which would be the raw parameter values. So the relevant object is a function the parameters represents. Distinct parameterizations can induce identical outputs, so controlling parameter motion is not intrinsically meaningful. Here's a toy example. If the model output is a square, say y equals x squared, then x and negative x are different parameters, but they produce the same output, since x squared is always equal to the square of negative x. These symmetries appear in modern networks. In transformer dot product self-attention, the score matrix depends on WQ times WK transpose, and you can always fit an invertible matrix in the middle that cancels and gives the same output. So your parameters WQ and WK are not uniquely identifiable just from the outputs. Likewise, in the ReLU activation function, you can just pull out any positive scalar and absorb it into the weights. In all these cases, large changes in parameter coordinates can still leave outputs, hence loss, unchanged. So a trust region defined in parameter space is not invariant to reparametrization, whereas a trust region defined in output space is. Therefore, given that the trust region for the loss is defined in the output space, we impose a bound, but a naive fixed bound like this is still brittle to reparametrization. For example, for our linear layers delta y equals delta w times x, you can just scale the input endlessly, which will also increase the norm of the output arbitrarily. So a more sensible approach would be to compare it to the norm of the input. So delta y has a norm less than or equal to eta times the norm of x. This ensures scale invariance under a positive scaling. And to avoid an explicit dependence on x while still bounding for all inputs, we can bound the worst case, which is precisely the operator norm. To recap, first, the loss is defined on outputs, so the trust region should be a norm on outputs. Second, but the output depends on the input, so we should account for its scale in the bound, giving us scale invariance. And third, to enable a closed-form solution without an explicit dependence on the input, we bound the worst case, which is a bound on the operator norm. Now that we've simplified the problem significantly, let's solve for the muon update. We want to figure out which increment delta w we should pick to minimize some loss on the parameters induced by the chain rule through our activation outputs. Once again, we use a linear approximation for our loss function. And now, this simplified problem is possible to solve analytically. For convenience, let's denote the gradient as g. Let's take the compact singular value decomposition, or SVD, of g. Now we just do some algebraic simplifications, substituting delta for negative delta w over eta. Remembering that uk and vk both form orthonormal sets, we can analyze each case over k independently using the Cauchy-Schwarz inequality, or in general, Holder's dual norm inequality. We can now sum these orthogonal solutions together, and this gives us delta equals uv transpose. And because all of the singular values are 1, then the maximum singular value, which is the spectral norm of our matrix, is also 1. This means, to solve our linearized problem, we need an efficient method to normalize the singular values of our gradient matrix. This function is called the matrix sinum, or also the polar factor because it's the orthogonal part in the polar decomposition of a matrix. Similar to the angle of a complex number in polar coordinates, it only encodes the directional component, not the size. We can also write it only in terms of the original matrix. Suppose G is a wide matrix, then the polar factor of G is the inverse square root of GG transpose right multiplied by G. If the matrix is not invertible, then you can use the Moore-Penrose pseudo-inverse. Again, we can check the derivation by plugging in the compact SVD. Now, as you might guess by now, this is the part that will involve the famous inverse square root algorithm mentioned in the title. The genius trick that makes this idea work is the ability to approximate functions using polynomial iterations, which only require multiplications. This is a super prevalent trick in numerical analysis, and was recently popularized for matrices in the shampoo optimizer. Newton's method is an algorithm to find the zeros of a function, but you can also use it to solve equations. If I have an equation f of x equals g of x, then I can subtract g of x on both sides to get f of x minus g of x is equal to 0. And if I define a new function, then I've simplified the problem into solving h of x equal to 0. How does Newton's method work? Our goal is to find the zeros to some function h. So we solve for x in the equation h of x is equal to 0. In general, h of x can be very complicated, so solving this equation exactly is either hard or even impossible. But you know what isn't complicated? A linear equation. You guessed it, Newton's method also takes a linear approximation of h at our current point xn. It's a constantly recurring theme, so instead of setting our original function h of x to 0, we set this linear approximation to 0 instead. And this is very easy to solve for x. Of course, if h is nonlinear, then it probably won't be 0 at this new point. But we might have moved closer. So assuming the process goes well, we can just keep iterating over and over until our value becomes close enough for what we need, such as h of xn less than 0.001, let's say. Now that we have Newton's method, how do we compute the inverse square root in a fast way without directly dealing with inverses, which are slow to compute? Well, let's start with the real case. Let's say we want to find the inverse square root of a fixed number y, and we'll call this new number x. Since y is a fixed number, as we said, our goal is to compute x. So using Newton's update, define h of x as this function, and then the derivative is negative 2x to the negative 3. After churning some algebra, our final update is x new defined as 3 halves x minus 1 half x cubed times y. Now we're ready to explore a crucial component of Muon, which is approximating the polar factor fast on GPUs. So to do this, we want to convert the heavy lifting into matrix multiplication. Remember that we wanted a map to approximate getting rid of the singular values. Now, researcher Jeremy Bernstein realized that odd matrix polynomials act only on the singular values of the input matrix. Without loss of generality, we can assume G is a wide matrix, so it has more columns than rows. Otherwise, we can just transpose it. When you multiply 3 copies of the matrix together with the middle one transposed, the semi-orthogonal matrices in the middle cancel out, and this process can be repeated over and over. Our goal, then, is to approximate a matrix polynomial that maps the singular values to the identity matrix. Therefore, its scalar counterpart is mapping any non-zero singular value to 1. Since our polynomial is odd, we can think of the sinum function over the real numbers. Now, the interesting part is that Bernstein initially used exactly the cubic iteration for the inverse square root with target y equals 1. So that x will converge to the inverse square root of y, which is 1. And this is the original idea presented in the documentation on the Modulo website. So when spamming this iteration, we do need to check that the singular values lie in a radius of convergence. For this polynomial, it's square root of 3. So one way we can guarantee that the singular values lie in this range is by using the inequality of the operator norm always being at most the Frobenius norm. So dividing each entry of the matrix by its Frobenius norm ensures that the singular values lie in the unit interval. In practice, it turns out that we don't need the singular values to be exactly 1. Even a rough approximation is good enough. What's more important is the convergence rate to reduce wall clock time. The original Muon implementation constrains the singular values between 0.7 and 1.3 in order to allow more aggressive convergence of smaller singular values, which is done by maximizing the coefficient of the linear term, which grows fastest for singular values in the unit interval. And using a numerical search, they came up with the coefficients 3.4445, -4.7750, and 2.0315. So we've seen how Muon lives or dies by one subroutine. Given a matrix G, we want to approximate its polar factor cheaply using only general matrix multiplications. Now, two recent improvements attack two different parts of that bottleneck. Polar express, which changes the coefficients of our polynomial on each step, and turbo Muon, which uses a different preconditioning than just naive Frobenius normalization before iteration. So far, we've been using one fixed odd polynomial over and over, like the tuned quintic Newton-Schulz. And while that works, it is a one-size-fits-all choice. Polar express leverages dynamic coefficients Fourier quintic polynomial. Remembering that odd matrix polynomials only act on singular values, the matrix problem reduces to a scalar approximation on the interval from L to 1 after pre-processing. So, in the Polar Express paper, the authors looked at the worst case for each iteration and derived the minimax optimal coefficients. In better float 16 precision, they also divide by a small safety factor like 1.01, so rounding does not push you outside of the stable interval. And they include small stabilizers so that the minimax polynomials behave nicely in low precision. So overall, it's the same compute pattern as the original Newton-Schulz, but the coefficients change every step, and the schedule is chosen to be optimal per iteration. This next trick does not change the polynomial iteration, but the pre-processing instead. So in our original Muon implementation, to bound the spectral norm, we divide each entry of our matrix by the Frobenius norm. But of course, this is a very naive and crude approach because we treat everything uniformly. Turbo Muon adds a cheap column scaling that they call the almost orthogonal layer. The insight is that in the polynomial iteration, you already compute the gram matrix so that you can reuse this computation to scale each column using an E1 row sum of the gram matrix. Now empirically, this often lets you drop one polynomial iteration, for example from 5 steps down to 4, while keeping similar quality. For reference, the Kimi K2 model used around 230,000 training steps, and Muon approximates the polar factor on every single training step, so that's quite a lot of gains. Let's now recap the Muon optimizer with some common tricks that we use for ML optimizers. In the trust region picture, each step chooses a descent direction from a local approximation. In deep learning, the gradient is typically estimated from a mini-batch, so the stochastic gradient is noisy and can vary noticeably from step to step. Momentum reduces this noise by accumulating gradients over time. Heavy ball momentum maintains a buffer that puts an exponential moving average on the past moments. This way, when the gradients are consistent, they reinforce, but when they are noisy, they average and cancel out. A closely related variant is Nesterov momentum, which uses a look-ahead to predict the next buffer. What changes for matrix parameters? Remember, for the matrix case, if we take the linearized subproblem and impose a trust region defined by a spectral norm ball, then the solution is given by the polar factor of our gradient. In contrast to the vector case, instead of normalization by a single scalar coefficient, we need to normalize the singular values of our gradient matrix. But this is now a nonlinear process, so we have to be careful about weight decay, unlike in the vector case. Muon is therefore best understood as a two-stage procedure for matrices. First, construct a matrix direction using the same momentum machinery as momentum SGD. Then, you project that direction onto the operator norm truss region boundary using the polar factor map, which is nonlinear. This construction gives us scale invariance similar to normalized SGD in the vector case. The Muon optimizer was developed in October 2024. Its name comes from the components that make it work: moment, orthogonalized by Newton-Schulz. It has garnered a lot of attention and excitement from the machine learning community for working so well in practice. Here are some example papers in the Muon ecosystem. First, Kimi Labs published 2 different papers which validates the performance of Muon at large scale, with their Moonlight 16 billion parameter mixture of experts and in actual production with their Kimi K2 model. And they use some additional important tweaks that allows it to work at large scale and also to reuse AdamW hyperparameters. Scion formalizes the use of linear minimization oracles in Muon and develops updates for several choices of norms with considerations for hyperparameter transfer. And it's closely related to the precursor paper, Old Optimizer, New Norms, and Anthology by Bernstein and Newhouse. Next up, AdamMuon and NorMuon combine ideas of AdamW's second moment state with Muon. And NorMuon is even used in the modern NanoGPT speedrun. Finally, a recent paper, Tion, Muon with Tensors, which takes Muon from matrices to tensors, stacking several linear layers together to orthogonalize their updates jointly.